Hi everyone, so today we're going to continue on our discussion for 11.2 complex solution. So last video we get to define the complex exponential function, and we learned that there are a few important properties that make our definition of the complex exponential function really nice and fit into our previous definition. So with or established rule for exponential function already. So first one is that the cosine x plus I sine x part does not alter the magnitude of the complex numbers, so which is nice because it has a unit length. And when you multiply two complex exponential function together, it follows the same rule as if you add the exponent together, which is also nice because that's what you know how to deal with exponential function in general. So you don't have to learn new thing. It just fit into the old definition. And three, probably the most important part, is the integration and the differentiation of e to the complex exponential function. We find out that it actually still follows the same exact rule, just like we would be with real numbers. So therefore, which we arrive in these two formula for the differentiation and the integration rules, and they work out exactly the same way as how we normally would know them, which is great because that means that we should be able to do the same thing with complex root and using them as a solution to our differential equation. So what I want to do is, before I kind of state theorems that would incorporate complex solution into our theorem 11.1.1, let's show you an example first. So here's a very simple example. Let's say we have this equation, and we're going to try to solve this. We're going to try to solve for y double prime plus y equal to 0. Okay, we're going to try to look for a general solution. So how do it work? So, well, no different than before. The first thing I'm going to do is I'm going to rewrite that into a differential operator form. So, just a quick recap. So this is our differential equation. This is our differential operator form of the differential equation. Oops. And then what we have, well, based on this, we have our characteristic equation. This is our associated characteristic equation. And it is from the characteristic equation that we attempt to solve, to form the solution set to this differential equation. So notice that because r squared plus 1, therefore become r squared equal to -1, r equal to plus or minus I. So that is our characteristic root. In this case, there are two, and they are complex. And because they're complex, they have to be conjugate of each other. So therefore, will never be repeated roots. So you, unless you have 4 roots, then you could have repeated complex root. But if you only have 2 roots, then they have to be conjugate pair. So now the question comes down to how to write the solution to this thing. Well, guess what? Theorem 11.1.1 still apply, even if the root is complex. Okay, the only difference is that we don't know how to deal with the complex exponential part, but now we do, so we can go and write our solution. So according to theorems 11.1.1, the solution set should be this. Y equal to C1 e to the ix plus C2 e to the negative ix. Okay, so now what happened is we now actually have a complex exponential function in both cases. So what would the solution look like? So we can actually expand this a little bit, and then I'll show you what happened. So that would equal to C1 e to ix can be represented as cosine x plus I sine x. plus C2. E to negative ix would basically equal to cosine negative x plus I sine negative x. Okay, because negative ix is negative x times I, technically speaking, or I times negative x. So therefore, we're plugging negative x into our CIS function, CIS function. Now, once again, you probably don't realize all this trigonometry involved. So there's a trig identity that tell me that cosine negative x, because cosine is an even function, cosine negative x is the same as cosine x. But sine is an odd function. Therefore, it becomes negative I sine x. So now what? That look okay, right? But notice that if I look at this, also remember the following. Okay, because this is a second degree differential equation, we should have only two terms or two vector in our basis to span the subspace of this solution set. And we do. Right now, what we do have is cosine plus I sine, cosine x plus I sine x, and cosine x minus I sine x. But they are pretty complex in its own and to use as basis. So is there some way to simplify this? So let's try. So this would equal to C1 cosine x plus, I guess, IC2 sine x. C1 sine x, I'm sorry, C1 sine x, plus C2 cosine x minus IC2 sine x. So now if you look at this, notice there are two real term and two imaginary term. So I'm going to go and combine them together. So therefore this becomes C1 plus C2 times cosine x plus, and I'm going to factor out I sine x from both of the last two terms, and so therefore become, or actually factor sine x from the last two terms, so become IC1 minus IC2 sine x. So therefore, look to me like we have a coefficient, then cosine x, plus another coefficient sine x. So in that case, why don't we now rename this A1 and rename this A2? Now notice here, I did not have an I next to A2, even though there are I here. The reason here is because A2 itself can be imaginary. So I don't have to specifically have an I in it. I just have to now allow the coefficient that we use to be real or imaginary. Now, unlike if you have a real characteristic root, then the coefficient in front of the function must be real. But if we now have complex characteristic roots, then that opens up the possibility for the coefficients to be complex also. So in here, what I have will be this. Y equal to A1 cosine x plus A2 sine x. So make a mental notes for yourself. A1 and A2 can be complex. And notice that that become our solution, which conform to what we expect. It has two terms, and therefore is a dimension 2 subspace. Now, to see that this is true, what I'm going to do is, let's go and show that this a function in this form will satisfy our differential equation. So how do I do that? Well, I need to find the second derivative. So I'm going to do and find my first derivative first. That will be negative A1 sine x plus A2 cosine x. And if I differentiate one more time, y double prime become negative A1 cosine x minus A2 sine x. So now if I take y double prime plus y, that become negative A1 cosine x minus A2 sine x plus y, which is A1 cosine x plus A2 sine x. Notice that that cancel with that cancel with that, and therefore give us 0. and that show that this equation, this solution set, this solution or function in this form will satisfy our differential equation. So now come the important question. So now, how does that help us identify what the solution would be? Well, now we can expand our theorem 11.1.2 into this new theorems. Theorems 11.2.3. Yes, I know, that's my first theorem in 11.2, but yet it's already designated to be 3 because 11.2.1 and 11.2.2 are actually some of these definitions that we use to define the complex exponential function. So I didn't designate them to be with the numerical designation. That's why we didn't talk about it. So this is our first theorem, 11.2.3. So it states the following. Okay, and this is probably the theorem that we're going to be using from this point on until we have a new theorems later on in the end of 11.2. Which is going to be 11.2.4, and that would generalize even further. But for now, let's talk about what happened to this theorem first. So let's say we're given a linear constant coefficient differential equation in the form of let's say y double prime plus by prime plus cy equal to 0. So I didn't say those adjectives, but you know that this is a second order and it is also a homogeneous differential equation. Okay, and so this equation would have a characteristic equation. Its characteristic equation is r squared plus br plus c equal to 0. And let's say we let r1 and r2 be the characteristic root. So now come the important properties. What would happen to these two characteristic roots? So if you recall learning it, so see here where things kind of come in full circle. If you remember learning it in Algebra 2, you learned this concept called nature of the root, which basically talk about what kind of roots do we have based on the discriminant of the quadratic equation. So now come the important part, because we don't care what the roots are, but that's for a specific problem. But we kind of do want to know what types of roots we have, because that would dictate how our solution look like. So if you recall, there are basically 3 different scenarios. So we're going to talk about all 3 of them. Case number 1, if b squared minus 4ac, but in our case a is 1, so I'm going to just say 4c, is greater than 0. Then what we know is this. Then R1 and R2 are real. And we know they are not equal to each other. And therefore, so the solution to this differential equation, the solution set, or the solution to this differential equation would be in the form of y equal to c1 e to r1x plus c2 e to r2x. So that becomes our solution if our characteristic roots are real. 2. If b squared minus 4ac, but once again a is 1, so I'm just saying 4c, is equal to 0, then what we know is that R1 and R2 are still real, and they are equal to each other, which I'm going to call them both R without the subscripts in their equal. And in that case, the solution is y equal to C1 e to Rx plus C2x e to the Rx. So no surprises there because we already talked about double roots. Here comes the interesting one, which is new. What if we have complex roots? 3. If b squared minus 4ac, or 4c in our case, is less than 0, then what happened is, then R1 and R2 are complex, not real. And let's say we define R1 to equal to a plus bi, and R2 is equal to a minus bi. Remember, they have to come in conjugate pair. So there's no negotiations here. If one equal to a plus bi, the one must be a minus bi. Okay, it's impossible for them to not be conjugate pair. And so, what would the solution look like? So the solution is actually in this form. It's actually in the form of y equal to C1 e to the ax cosine bx plus C2 e to the ax sine bx. And that's our solution. Now, some of you, a very common mistake that students always ask is the following. Shouldn't there be an I for the sine bx part? The answer is no. The reason why, because C2 is an arbitrary constant, and in this case, we just simply have to understand that C2 could be complex, and therefore automatically have the I in it once we find it. So we don't need to specify that there's another I in it. Because when you put an I in front of C2, it just basically forms an arbitrary constant, just like before. Same exact reason why you would not put 2C2, because 2C2 would just be the same as just some other number, C3. Okay, so there's no reason to have that extra I attached to a constant that we don't know. So it would just be C1 e to ax cosine bx plus C2 e to ax sine bx, whereas C1 and C2 have to be real. So important to make a note for yourself if you want to. In the case of 1 and 2, both C1 and C2 are real since the characteristic roots are real. But if the characteristic roots are complex, then the coefficient now can be complex. Okay? So, if you want to make sure you can write a note for yourself. If R1 and R2 are real, then C1 and C2 are real. If R1 and R2 are complex, then C1 and C2 can be real or complex. Which is the reason why you don't have to put an I next to the sine bx, because it's redundant. Now then, what happened to C1 and C2? Well, it's the value, whether they are real or imaginary, the values for C1 and C2 will be uniquely defined by using what we call initial condition. Can be uniquely determined by using initial condition. And the initial condition is exactly the same. y of, let's say, some number x sub 0 equal to a, and y prime of x sub 0 equal to b. Remember, they are initial condition, therefore they must be on the same exact x value. So this would be our theorems for a while until we're ready to move on to talk about, I guess, higher order differential equation, which we will, but probably not today's video. So I only have about 10 more minutes. So I'm going to maybe show you a couple more example, okay, that hopefully would can help you see how this theorem is being used. And in actuality, you're not going to actually look for the discriminant. You're just going to try to solve for the root and just see what the roots are. Okay, but it is nice to have the discriminant so that we can use it to define. So let's start with this example. Let's say, how about we just going to try to find the general solution of this equation: y double prime plus 2y prime plus 5y equal to 0. Okay, so it's pretty straightforward. So here's my equation, which have this differential operator form, and which have this characteristic equation. And here you shouldn't be too hard for you to figure out that there's no two integers that multiply to 5 and give you 2 in the middle. The only pair of integer that multiply to 5 will be 1 times 5, which either add up to, in this case, have to be either both positive or both negative. So they will both either give you positive or negative 6 in the middle, and can be positive 2. So therefore, this is technically not factorable. Does not mean it doesn't have root. It would always have 2 roots, just real or imaginary. And since it's not factorable, quadratic formula is how we're going to approach this. So I'm going to go and do that. So that would mean that r must equal to negative b plus or minus square roots b squared minus 4ac over 2a, which is just 2. Notice that this part is negative, therefore indicate we have complex roots. So r equal to negative 2 plus or minus square root of negative 16 over 2. So that's negative 2 plus or minus 4i over 2, or negative 1 plus or minus 2i. So that become my characteristic roots. And as I say, it has 2 conjugate pair. So now what should the roots be? Well, simple. When I try to write out the complex characteristic root general solution, all I need is to identify the a and the b value. Okay, so notice that I can think of R1 and R2 be a plus or minus bi. And so the a and the b would be, in our case, negative 1 and 2. So notice that in this scenario, a equal to negative 1, b equal to 2. So now I'm ready to write out my solution. My solution is y equal to c1 e to the ax, which become negative x, cosine by, so bx, which is 2x, plus c2 e to the ax, which is negative x, sine bx, which is 2x. That form our solution. Good. Now we can definitely do another example. So how about we do one more, and hopefully I have enough time to finish it before we hit the 30-minute mark. How about let's solve this one. Solve the initial value problem, IVP. Let's say we have the equation y double prime equal to y prime minus y, and y of 0 equal to negative 2, and y prime of 0 equal to 1. So we'll go through our problem. So the first thing I need to do is I do need to kind of put my equation into what we call normalized form. So that would just be y double prime minus y prime plus y equal to 0. And so the differential operator form would be d squared minus d plus 1 of y equal to 0. And the characteristic equation is r squared minus r plus 1 equal to 0. And now what I'm going to do is try to solve for the characteristic roots. So r equal to negative 1, which is 1, plus or minus square root. B squared, which is 1, minus 4ac, which is 4. So therefore it becomes 3, negative 3, over 2. So that means that r actually equal to, now notice how I'm going to write this, because I want to put it into a plus bi form, so that I can identify a and b to finish the problem. So therefore, I'm going to write this as 1/2 plus or minus, I would say square root of 3 over 2i. So that's my characteristic roots. And this would be my a, which is 1/2. And this would be my b, which is radical 3 over 2. So now I'm ready to write out my solution. My solution set would be y equal to c1 e to the 1 over 2x cosine rad 3 over 2x plus c2 e to the 1/2 x sine rad 3 over 2x. And that's my general solution. So now what I need is to find C1 and C2 using the initial condition. So I guess go ahead and give it a try. Let's see. So my first initial condition is y of 0 equal to negative 2. So what does that tell me is that we need negative 2 equal to C1 e to the 0 cosine of 0 plus C2 e to the 0 sine 0. Oops, I don't need that parentheses. Sine 0. So notice that sine 0 actually go to 0. So this thing go away. Cosine of 0 is 1. Okay. And e to 0 is also 1. So therefore, that's just automatically when that tell me that C1 equal to negative 2, which is nice. Okay, now here comes the tricky part, is to try to find the derivative of this thing. Because it's e to the 1/2 x cosine radical 3 over 2x and e to 1/2 x sine radical 3 over 2x. And both of that's are products. So therefore, it's going to take a little bit of time to form y prime. So I'm going to do that. So y prime will equal to the following. So product rule to be applied. So it will be C1, let's say e to the 1/2 x multiplied by radical 3 over 2 and negative sine radical 3 over 2x plus C1 1/2 e to the 1/2 x multiplied by cosine radical 3 over 2x. So that's the product rule for the first part. Plus, I'm going to do the product rule the second part, same way, C2 e to the 1/2 x multiplied by rad 3 over 2 and cosine of rad 3 over 2x plus C2 e 1/2 e to the 1/2 x and multiplied by sine of radical 3 over 2x. So that's my derivative. Now, normally I would probably clean it up if I want to present y prime, but I actually don't care what y prime look like because I just simply want to solve for C2. So I do know the following. If I plug in 0, y prime of 0 would equal negative 1. So therefore imply negative 1 equal to, now remember, because I plug in 0, sine would go to 0. So therefore, this first term is out. This second term right here, both cosine 0 and eta 0 would be 1, so therefore become 1/2 C1 plus this term right here would stay, therefore become radical 3 over 2 C2. This term with the sine radical 3 over 2x would go to 0. So therefore that one is gone. So that's what I just have. And I already know C1, so I'm going to plug that in. So if I plug that in, I'll have -1 equal to -1 plus radical 3 over 2 C2. Notice that these two things cancel out, leave you with C2 or radical 3 C2 equal to 0. And therefore imply the C2 is 0, which is good. That means that terms go away. So now I can write out my solution. My solution is y equal to -2 e to the 1/2 x cosine rad 3 over 2x. And that become our solution. All right. Unfortunately, that's all the time I got for today. So I guess I'll stop right here. And we'll continue on our next video. All right. Talk to you guys. Bye-bye.